So now I want to talk about an important aspect of learning. Well, I would say generally learning on graphs or using, the forward and backward approach to deep learning training on graphs. And that's basically the following idea. We learned how graph neural networks are defined. And the graph neural network might require the full graph to come up with the label of a node, the end result, the output that is assigned to a node. Okay, but oftentimes these graphs are large, too large to be applied, in our standard hardware, in standard GPU. Okay, so what do we do in these cases? And we had a solution for standard learning. It doesn't apply, in a naive way to graph learning. So first, let's look at some examples. These are the from standard benchmarks, RHEL-Bench, DB 4DB Infer. We talked about these, the one from Stanford, one from Amazon, and you can see here that some of these databases have millions of tuples or billions of tuples or tens of millions of tuples. And then, each tuple becomes a node and a node with an embedding. And you have several layers. Okay, so several uh, layers of these embeddings. These can become quite large to execute, as a one big monolithic object on our hardware. Okay, and that's a problem that we need to deal with. Let me explain it in the way that is more accurate. Say. Okay, so we have this situation of a single graph G. Okay, one big graph, and our training is a set of nodes along with their labels. Okay, so we think of a node classification. It's a very standard situation. It arises, for example, if you have one database, one big relational database, and your task applies to one of the tables. Okay, so you have several tuples along with their edges for your training. Okay, and the entire full database is there for computing the GNN, basically. Okay, now in principle, we can learn the weights by applying gradient descent or Adam optimizer on the full graph. No problem if the graph is small. Okay, um, but a graph may be again too big. So applying full batch computation on the full graph might be ineffective. Okay, and so we want to do what we did in the other models of deep neural networks, basically apply batching, mini batching, or stochastic gradient descent, and then with these mini batches, we can use whatever we want, gradient descent, or a atom optimizer, or whatever. Okay, but here is where graphs are different from tabular or matrix learning. Even one batch computation may involve a large portion of the graph. It's not like just these nodes of the batch that we are using for the batch. We also need to take the neighbors and the neighbors of the neighbors and so on. And that might involve a graph that is too big. Okay, we can see here examples. We start with one node of the batch. We take the neighbors and then the neighbors of the neighbors. And quickly we are becoming, very large. Okay, by following a step. That's basically called the small wall phenomenon. That after a few steps, a small number of steps, you reach essentially all of the graph. Okay, so using the samples really doesn't help. Okay, if we have several steps and we need to do something. Okay, and basically we would like to say we use batches and we control the sizes of the batches. So again, we have the set of examples, node vi label yi, and now we take batches from these nodes, okay, B, but then our formula involves the LHOP neighborhood. Again, this can be very large. Okay, so how does the batch help us? Okay, now you can think of, say, take a random subgraph or a random set of nodes and edges. But if you just do it so, without really accounting for the structure of the graph, you can imagine that you often get graphs that are useless. For example, you have disconnected fragments. The GNN cannot reach, from the target to the input or from the input to the target because everything is disconnected. You need to do so in a way that is aware of the GNN in order to allow it to activate and to effectively learning or produce something that is meaningful. Okay, so we need to apply GNN aware sampling techniques in order to produce a batch. And we're going to look at three types of sampling, basically three types of producing mini batches: node-wise, layer-wise, and graph-wise. Okay, and I'm going to talk about each of these in the next slides. Node-wise. Uh, so the general idea is that we have our set of nodes in the batch. Okay, for every node vi that we have in the batch, we select a random set of neighbors. Okay, for every node independently of the others. Okay, and we compute these for the lower level, not for the higher level, for the lower level. And why so? Because when we apply the GNN, every layer aggregates information from neighbors, assuming that they went through the lower layers, the previous layers. So that's why we sample nodes, sample neighbors from the higher level to the lower levels, not the natural way, the backward way, not the forward way. Okay, and you continue sampling nodes until we reach the input layer. A prominent example is Sage. Here we select a fixed number of neighbors for every node. Okay, and in terms of the implementation, you can define the number of nodes that you're sampling in each layer. The first step chooses 50 neighbors. The second step chooses 10 neighbors and so on. Okay, so we start with the target batch, okay, B, call it BL, and then we create a batch for the lower level, okay, BL minus 1. How do we do this? Well, we use the previous batch, BL minus 1, BL, okay, we start with BL minus 1 equal BL, and we add to it a fixed number of random neighbors for every node in the batch, okay, and then we continue doing so for the L minus 2 all the way to the input layer. Okay, so every layer has more nodes and it includes, it's basically the higher, the upper layer plus neighborhood. Okay, and then as we had when we compute the layer HK, basically, we use the neighbors of the lower layer, but restrict the learning and the aggregation, everything basically, only to the neighbors that are in the lower layer. And the node selected for the lower layer, BK minus 1. Okay? And so that was Sage. Then there was a follow-up work, VR GCN, where basically VR stands for variation reduction, where they basically showed how to optimize the sizes of these samples with respect to the utility, okay, or the sizes per layer. I will show that this actually gives a good results, but I'm not going to really explain what it does. Okay, so this is the full Sage algorithm. You can see that here they basically produce these bees, okay, these batches. This is from the original paper. So they define the sets of nodes, the bees BK from the nodes by sampling, okay, neighbors, okay, and then when they apply the uh, GNN, this is a standard GNN, right? Message passing GNN. Aggregation, activation, and so on. And here they also have a normalization layer. They consider for the neighborhood of you, for the neighbors of you, only those neighbors that are selected for our bees, for our batches. Okay? So this is the idea, quite simple. They use the small graphs in the as the default of the experiment. They tried this approach with different types of MPNNs with different aggregation functions. Something that is unusual is that they use LSTM. LSTM is is a natural language um, processing technique um, where basically it does account for the order. Okay, so if you think of it, using LSTM is not permutation equivariant like using something that is commutative, like sum or max or a thing like that, or the convolution that they use here. And they also deal with that in the uh, paper, basically reducing the level of equivariance. And the reason they do it is that they actually get good results out of that. Okay, so these are experiments from the paper, okay? And what we see, well, they compare between the different aggregations. See, LSTM gets good numbers. And they also compare it to deep walk. Okay, at the time of the paper, deep walk was state of the art. And then they test not only the quality, okay, the accuracy of the functions, but also the execution times. And that's an important case for them. So they show, that their training takes longer than deep walk, okay, but their inference time is actually much better than deep walk. And the reason is that when they apply the function to the or the downstream task to the nodes, well, in deep work they need to sample neighborhoods and compute the embeddings, and here they just apply the GNN to these small neighborhoods. So that's actually much faster. You see, this is a logarithmic scale. Okay, here they show how the neighborhood size actually affects the quality of learning and their runtime. So you see, for example, that well, it starts from 0.77, so even small sizes give you some good results on this micro F1, which is a measure for clusters. Um, but you see that you have this number, say 20 nodes of neighbors, where using this number gives you a very good balance between the execution time, okay, and the quality, okay, and the accuracy of the model. From this point all the way to using 75 nodes, you don't gain too much accuracy. So there is a sweet spot for the sampling size. Okay, now let's talk about layer-wise sampling. We talked about node-wise sampling, where we start from a node and produce neighborhoods from that. Let's talk about layer-wise sampling. And the idea is again that for every layer we compute the nodes from that layer, but unlike node-wise, in layer-wise we use the full set of nodes in the layer to compute the lower set of nodes for the lower layers. Okay, so what's the difference? We do not just look at every node independently and choose neighbors for that node, but basically we say, okay, what is the set of all nodes that was selected for BK? From that, let's select a good set of nodes for BK minus one, accounting for the fact that, for example, some nodes are neighbors of multiple nodes from the previous layer, so it might be beneficial to take these. Okay, and several papers that looked at this approach fast, GCN AS, GCN. Um, One uses an independent well distribution of nodes, and that applies to dense graphs. We're likely to hit neighbors, and ASGCN actually uses some conditional probability or joint probability between layer k and layer k minus one, with basically the motivation or the intuition that if a node is a neighbor of many nodes from the previous layer, from the upper layer, then it has a higher probability of being selected because it's actually useful to take this node in order to train to evaluate the upper layer. So that's the idea. Here I just put the two techniques pictorially, again trying to emphasize the difference between them. Node-wise, we take every node and we compute a set of neighbors, or the samples for this node from the previous layer, regardless of what we did for the other nodes. That's node-wise. And layer-wise, we take the full set of nodes for k minus one and produce from that the set of nodes for layer k. Again, from the full batch to the full batch. Okay, that's the idea. The last one is graph-wise sampling, which is really different from a node and layer-wise. And the idea there is that we are producing upfront random subgraphs, GI, of our graph G. And that's it. Each GI is now used as its own batch, as its own example. We use it. We use the full GI, full GNN on the full GI, as if we're not doing mini batching. Okay, so similarly to the original idea of mini batching, so very simple. No need to this is also insensitive to the model. This is, uses the model as a black box because we don't care about the layers of the model. We just say, okay, choose a random graph. So this is a really a simple technique, and you see that the experiments show that it actually works. One might say surprisingly. Okay, cluster GCN is really using the idea that what it is that we want from such a random make graph. Well, we want it to lose as little information as possible. Um, Ideally, you don't need to do anything because the graphs are disconnected, so you just take the connected components of the graph. But this doesn't apply. So what do? You're trying to cluster, basically, to take parts of the graph that minimize the connections, the number of connections between different parts. That's exactly what we do in graph clustering algorithms. So their idea is to use standard graph clustering algorithm. Here they use the Metis, and that's your basis for the batches. Okay, and they tried two techniques. In one, every such a cluster is the batch. Okay, so they choose a random cluster, and that's going to be our batch or a mini batch. And in the other, they're combining several together. So you say, okay, choose one, choose second, choose third, and the union of these plus the connections between them, the original connections between them, are going to be our graphs. Okay, our mini batches. Graph Saint is not based on clustering. It is really based on choosing random graphs, and they look at choosing random nodes and taking the induced graph on them, or choosing random edges, or choosing random walks. Okay, and um, they use different ways of normalizing these because they introduce some bias to the graph. Um and each of these is based on some independent sampling. So you choose independently nodes, edges, or random walks, but these are not IID samples. Okay, it may be the case that some nodes have a higher probability, like they have high degree. Uh, so the distribution, which is not necessarily uniform, is pre-computed, and you're using this distribution in order to choose your random graphs. Okay, so they run experiments on the biological domain, protein-protein interaction, and also on social networks. So these are the PPI and Reddit data sets. They look at the they measure basically the quality, may it be rock AUC or F1. And well, you can see, these are interesting examples. Well, they're much better than Graph Sage. It's not like Graph Sage is zero. Okay, these graphs start with here they start with 0.9. Here they are lower. So they say that to show that they are much better than Graph Sage in these tasks, and they are comparable very much to this. Next generation of Graph Sage, which is VRGCN. Okay, Graph Saint. Well, this I took the pseudocode from the algorithm from the paper, basically to show that up to this idea of we're building a graph, sampling a graph from the big graph G with some sampling technique, node, edge, random walk. Other than that, this is just standard neural network learning. We apply the construction to this graph. We define the model for this graph. Okay, then we apply the forward propagation, nothing special, and then backward propagation with some standard loss and update the weight. This is exactly the same thing that we have in a standard model. Nothing here is special, again, except for this part where we say you need to sample a graph. Okay, that's the main message here. And they compare GraphSane to basically all of the models that we've seen so far, GraphSage, also things that are not using mini batching. And well, they show that basically the graphs show what is the quality per training time. So you want to reach quickly the higher numbers, and you see that the red lines of graph saying they're actually quite good compared to the others. And yeah, that's basically it. And that's all. The next part, which is also the last, is going to talk specifically about this problem of link prediction, which has a scaling issue, significant scaling issue by itself.